Hello there, welcome to the fifth of the live sessions. Again, like last week, it's just before a big exam. In this case, it's chemistry tomorrow. So obviously you might not be watching this live again. Once I'm finished, the PDF document will be placed on the website, and you can see the URL on the screen. So the PDF itself, as I said, will be placed on the website. You'll be able to download the questions, maybe try them out, and then go through them while watching the video. So we're just going to get straight into them with this question here. Now, the question asks, a smoke detector contains americium-241, which is a source of alpha radiation with a half-life of 432 years. State two reasons why americium-241 would be a poor choice as a radioactive tracer to be injected into a patient's body. Now, there may be more than just, of course, the two answers that I'm going to be talking about, but the main two, I would say, if you're looking for a radioactive tracer, in order to, as it says here, to be injected into a patient's body, it needs to be penetrating enough in order for, if it's, let's say the radiation is being picked up with a gamma camera, it needs to be penetrating enough, of course, to then be detected outside the body. Something which emits alpha radiation wouldn't be penetrating enough. So, number one, tracers themselves. So, they should emit gamma radiation. I was going to write the symbol for gamma radiation there. And the second thing, of course, this is talking about a smoke detector. The half-life of this alpha source is 432 years. A great thing, obviously, for a smoke detector, because it means that someone doesn't need to take that apart and replace the, well, that would never happen, of course, replace the radioactive source, or obviously wouldn't need to be changing the smoke detector on a regular basis. That obviously what would happen for safety reasons. For a tracer, in order to reduce the risk of harm to the patient, then of course you would need to use something with a short half-life. So the two answers we're looking for in this one are that the tracer itself should emit gamma radiation, and it should also have a short half-life. So you would be saying that, of course, this americium-241, the fact that it's emitting gamma radiation, it obviously wouldn't be detected outside the body, and the half-life is far too long. So there we go, that's just a starter. Now the second part of this question looks like so. Now it says state two other uses of nuclear radiation. Now there are a few things I'm going over tonight, but I would say just make sure you're reading through your textbook or your notes. I'm not going to give an exhaustive list to this question or any of the questions. Now we've already mentioned in smoke detectors sometimes you'll use it would be this americium-241, an alpha source. Of course that is contained within a lead box. You should also know that, of course, alpha radiation would be absorbed just by 10 centimeters of air. So it's not very penetrating, as we'll talk about later. We've mentioned tracers, radioactive tracers, which, as we said, should be emitting gamma radiation, should have a short half-life. If you were asked for any other applications, you could be mentioning sterilizing medical instruments. So we know that radiation can cause harm to cancerous cells, so it can be used to kill cancerous cells. That's one thing. It can be used because it kills bacteria and germs, it can be used for sterilization. So it can be used to sterilize medical instruments. As we said, it can be used to destroy cancer cells. It could be used in a nuclear power plant, of course, to produce electrical energy. But as I said, just make sure you're looking through your notes, and this would be one of the things you would need to know, of course, the uses of radiation. Now at this point, I've just started you off with a quick question, but I would like to show a few slides. In fact, it sounds like a lot, but I'm going to get through them quickly And this is number 1 of 6, as I said. Sounds like quite a bit, but I'm going to try and get through those quickly. Now, first of all, as it says here, alpha, beta and gamma radiation can be emitted from an unstable nucleus. So here we have a nucleus here which is unstable, and in order to become more stable, what it's going to do is it's going to emit alpha or beta or gamma radiation. Before we talk about that, all radiation, alpha, beta and gamma, comes from the nucleus itself, and we should be familiar with this diagram of the atom. So what it shows is, of course, the nucleus at the center with positive protons, neutral neutrons and negatively charged electrons on the outside. Could be, of course, that we need to draw this diagram and this is one model of the atom that we need to know about. But as I said, all radiation, alpha, beta and gamma, comes from the nucleus itself. Now, having said that, we'll look at the first type, which is here, alpha radiation. Whoops, 2 seconds, this computer's playing up. There we go. So yes, alpha radiation shown here, and alpha radiation, this is one way in which that unstable nucleus may become more stable, by emitting an alpha particle. So an alpha particle contains 2 protons, 2 neutrons. Obviously, because of that, the alpha particle is positively charged. Okay? Being positively charged, of course, it could be deflected in an electric field. It would be repelled, of course, by a positive charge, another positive charge, attracted towards another, or attracted towards a negative charge. But within an electric field, it would be deflected because of its positive charge. There we go. So 2 protons, 2 neutrons. In other words, as it says at the top, a helium nucleus. So that's the alpha particle. Second one is the beta particle. Now remember, we said before that all radiation comes from the nucleus. This is an odd one because the beta particle is a fast moving electron, and of course the nucleus doesn't contain electrons. What's actually happened, you probably know this yourself anyway, is that within the nucleus, one of the neutrons actually converts to a proton, or turns into a proton and an electron. It's something we talk about in more detail with higher physics. We talk about something called the weak interaction, the weak force, but obviously not appropriate to National 5. So a neutron is converted into a proton and an electron, and the electron itself is ejected, and that is the beta particle. Now the beta particle is faster moving than the alpha particle, moves roughly 90% of the speed of light, and as we said, because it's an electron, it's negatively charged. Again, because that's charged, it could be, or would be, deflected in an electric field. At a higher level, again, we talk about the deflection of charges within magnetic fields, but only within electric fields in National 5. Last but not least, now remember we spoke last week about the electromagnetic spectrum. So it should be no surprise when we see this thing here, gamma radiation. Gamma radiation, as it said, is part of the electromagnetic spectrum, and we learned a mnemonic which allowed us to remember the order of the electromagnetic spectrum. And when we were going through the list, we started at one end with the radio waves with the larger wavelength. We ended up, at least the way it was drawn in the diagram I had, at the right hand side, the high frequency end. Of course, it could be drawn in the opposite order, starting with gamma on the left, moving towards radio on the right hand side. But the diagram we had radio waves on the left hand side, gamma rays on the right hand side, and gamma rays out of the electromagnetic spectrum, they've got the highest frequency. That's the high energy end we spoke about. And that's the thing, alpha particles and beta particles, they're made of stuff. As we said, beta particles are electrons, actual particles themselves, and alpha particles, they're made up of 2 protons and 2 neutrons. Gamma rays are electromagnetic waves. And as we said, they travel at the speed of light and they have no charge, so they wouldn't be deflected by an electric field. Now, two more to look at, and some of what's mentioned in the next slide or two will come up in a question that I'll be showing you later. Now again, this should be familiar to you. It's just comparing the penetrating power of alpha, beta and gamma radiation. Now, what it's obviously showing is that gamma radiation, gamma rays down here, they're by far the most penetrating. So easily be able to pass through a sheet of paper. Aluminium takes a much more dense material like lead, and quite thick lead as well, of course, in order to absorb the gamma rays. In fact, even with 2 centimeters of lead, they might not be fully absorbed. So gamma rays are by far the most penetrating, followed by beta particles, and that's of course to do with the speed at which they move, and of course their size. They're far smaller than alpha particles. Remember, we said alpha particles are made of 2 protons, 2 neutrons. Beta particles are just small, fast-moving electrons. So beta particles come after gamma rays in that they're the second most penetrating. Most beta particles would be able to pass through a sheet of paper. Not 100% of them, but most of them would. And it would take something, again, more dense, something like, as I've said here, around about 5 millimeters of aluminium in order to absorb our beta particles. And of course the alpha particles, because of their size and the fact that they're moving slower, they would be absorbed by a sheet of paper, as we said. And as I said before, could even be absorbed by roughly 10 centimeters of air. So it's important to know the penetrating power, to be able to compare the penetrating power of these 3 types of radiation. And last but not least, remember I said there were 6 of these and I wanted to get through them fairly quickly. The last one looks like this, and this is about ionization. So I've actually shown a diagram, and down at the bottom right, this is, at least to start with, a neutral atom. If that's a neutral atom, then of course it will contain as many negative electrons as positive protons. But the process I'm showing here is actually ionization caused by this alpha particle, and how the alpha particle can interact with this neutral atom. So obviously if this alpha particle is moving in this direction, very, very close to this neutral atom, because the alpha particle is positively charged, what it can do, and it's shown here, is it can attract an electron away from the neutral atom. Now of course, if this atom is neutral to begin with, because it contains as many negative electrons as positive protons, if it loses a negative electron, it then becomes positively charged. So in other words, becomes a positive ion. Now, the most ionizing type of radiation is alpha. And then would be beta radiation. And last, the least ionizing, is gamma. So of course, this is the opposite order to what we had before. Before, when we were talking about penetrating power, gamma rays were the most penetrating, then beta, then alpha. But in terms of ionization, alpha is the most ionizing, then the beta, and then gamma. Now, something I did say that next week, which would be the last, and technically this is the last of the actual lessons going through any of the work in order, talking I guess unit by unit. But next Monday there will be a short lesson, maybe half an hour I guess, just talking about a few things, maybe open-ended questions and so on, how to approach the exam and so on. In fact, I've been putting away the piece of paper and lost my my train of thought. One thing we'll talk about is my brain has gone. I'm looking at the equations we're going to look at later. I'll change the subject. Maybe hopefully I'll come back to what I was going to say at that point. One thing as well, which I didn't mention at the start, is the relationship sheet. We will later on tonight actually be talking about 4 equations, which the 4 radiation equations. Remember, in the website you can download a file called Help with the Relationship Sheet. So that is online, and of course lots of terms in those equations which you need to know. So I would have a look at that certainly in the week, within the final week before this final exam. Right, anyway, what I was talking about, as I said, was ionization. Oh, that's what I was going to mention. I was going to mention definitions. That was it. So yes, if you needed to know I'm glad that came back to me. If you needed to know the definition of ionization, I've got something up on the screen. So the removal of an electron from a neutral atom, leaving it positively charged. As I said, the lesson next week we'll maybe talk about a few definitions, the definition for current, voltage, ionization. One we'll mention later today, radiation weighting factor. So it came back to me, thank goodness. Right, that brings us to the next of our slides, which looks like so. It should be this one. Again, it's going to take me just a second to find the right one. There we go. Now, this is slightly different to most of the, it's a half-life question, most of the half-life questions you maybe be used to seeing. And it says the half-life of francium-223 is 20 minutes. Calculate the time taken for the activity of a sample of francium-223 to decrease to 1/32 of its original value. Now, of course, what's going to happen in one half-life is, of course, that whatever the initial activity of the source is, after one half-life, it will, of course, be half of that activity. So when I'm working out these questions, I usually start with the number 1. If it's a question which is talking about not mentioning, say, the initial activity and then a final activity after a certain time. If it's one of these which is talking about the fraction of the activity after a certain amount of time, I would start with the number 1. So this basically just represents 1 times the initial activity. Obviously, after one half-life, the activity would be a half of the initial activity. After 2, it's obviously going to keep halving. After 2 half-lives, it's going to be a quarter, and then of course we just continue until we get to 1/32. So we have 1/8 next. Half that, we get to 1/16. Half that again, we get to 1/32. And it's important, of course, at this stage not to count the numbers. We've got 1, 2, 3, 4, 5, 6, by the looks of it, 6 numbers, but count the arrows. And of course the arrows represent the half-life. So in one half-life, the activity has gone from its initial value to half of that initial value. 2 half-lives, it's gone to quarter. 3, 4, 5. So it's actually taken 5 half-lives to get to 1/32 of the initial activity. So the question, remember itself, said calculate the time taken for the activity of a sample of francium-223 to decrease to 1/32 of its original value, and it says at the top that the half-life is 20 minutes. So of course the time taken would be 5 half-lives, so 5 lots of 20 minutes is equal to 120 minutes, and that would be acceptable in this type of question. You remember, if we were using an equation, say Q equals IT, and we had to work out time, then of course the SI unit for time would be seconds. In this question, it is okay to leave that in minutes. Oh, sorry, I've made a mistake as well. Sorry, 100 minutes. Right. Let's see now the next question I'm going to find. Now, apologies for that mistake. Next question looks like this one here. Now again, it's another half-life question. What does it say? During an experiment, it says a total count rate. This is important. A total count rate of 340 counts per minute, or CPM, was recorded when a sample of iodine-131 was placed close to a Geiger-Müller tube and counter. When the experiment was repeated 24 days later with the same source, the total count rate was found to be 60 counts per minute. Background count rate was measured to be 20 counts per minute. Calculate the half-life of the iodine 131 source. So, the important thing is, well, of course, that that's the total count rate. So partly that's from the source itself, and partly it's the 20 counts per minute from the background. So of course the source count rate that would be equal to the total. That's what we've got up there. Total count rate minus the background count rate. Because of course the background count rate, that's not going to half. What will half, of course, in one half-life will be the source count rate, which of course can also be called the corrected count rate. So what we really want to do is to start with the initial corrected count rate or source count rate, and then keep halving that. So 340 was the initial total count rate. If we subtract, so that's 340, subtract the 20, which is the background count rate, and that means that the source count rate or corrected count rate, as I said at the start, is 320, and we just want to be keeping halving that number until we get to the final value. Now the final value, if I can find the pointer again, is it's not quite this number. This says that after 24 days with the same source, the total count rate was found to be 60 counts per minute. Again, of that, 20 counts per minute is the background count. So the actual source or corrected count rate would be 40. So we want to start off with our corrected count rate of 320 and keep halving that until we get to 40. Now, most questions wouldn't be quite as tricky as this. So most questions, it would actually be telling you the corrected count rate, or it would be a question where it's telling you an initial and final activity, and we wouldn't need to do this. So this is only if it's telling you the total count rate. So if it's telling you the total count rate, you would of course have to take off the background count rate. But most questions wouldn't be quite as complex as that. Now again, what we need to do is to count the half-lives, and we've got one half-life took us from 320 to 160, 2, and then 3. So we know that in 3 half-lives, the actual corrected count rate or source count rate has gone from 320 to 40 counts per minute, and we also know that occurred in 24 days. So 3 half-lives, that's 24 days, and therefore half-life is 24 over 3, and that means the half-life is 8 days. And there we have the answer. Now, there is another part to this question. In fact, there are another 2 parts to this question. So let me just find the next one. There we have it. Right, so the question says, same at the top, but part B says, state one factor which affects the background radiation level. Now again, this is a point where you should be looking to your notes, to the textbook, and so on. It's not something I'm going to write down, so just make sure that you do know some sources, maybe 2 which are natural sources of background or contribute to the background radiation level, and 2 which are man-made. So natural could be, say, the radon or thoron gas, which is coming from rocks or soil, or could also be cosmic rays. So those are 2 natural sources. And man-made sources could be, say, the fallout from nuclear weapons testing, or say even radiation used in medicine. And as I said, make sure that you've looked at your notes and you can name 2 natural sources, 2 man-made sources. Okay? Now, as I said, I wasn't going to write that up on the board in the next, or up in the sheet. The next part, I don't think I'll write down either. And as I said, next week, when I eventually remembered what it was I was wanting to say, next week we'll talk about some definitions. And this is one that you might need to, or you might be asked. So next week we'll talk about voltage, current, and so on, maybe power and so on, as well as general exam technique, open-ended questions, just for a quick final lesson. In fact, what I'll do is I'll mention two different definitions for half-life. Maybe just write one of them down then. So half-life, when it's saying part C, state the meaning of the term half-life. One could be the time taken for half the radioactive nuclei present to disintegrate. We spoke about, of course, this happening, that it's the nuclei or nucleus disintegrating and emitting the alpha particle, beta particle, or the gamma ray. So as we said, it's time taken for half of the radioactive nuclei present to disintegrate. Or the second thing, or the second definition I should say, is it's the time taken for the activity of the radioactive source to half. And there we have it. Now that's actually the last of the questions on half-life. Remember, on the YouTube channel there is a video which describes how to determine the half-life of a sample from a graph. So I would have a look at that one as well. And that's us now going on to the equations. As I said, 4 equations that I would like to look at. And again, before, there's just one question which remains, but before we actually try that one question, I'd just like to look at this first. Now, I don't mean to scare anyone, but quite a few terms contained, and terms which I guess up to this point maybe haven't come up, quite a few terms in these 4 equations. And as I said before, on the website there is a link to a file, a PDF document, which is called Help with the Relationship Sheet. And what it really does is it goes through, and it's in alphabetical order, the different letters, I guess, that you might see in the relationship sheet. So of course up at the top would be A for activity. Now the 4 equations we have are A is N over T, where A is activity in becquerels, N number of nuclei decaying in time in seconds. Excuse me. A second one, absorbed dose D is equal to energy E in joules divided by mass in kilograms. And another 2 equations, H equivalent dose is equal to D, which is absorbed dose, multiplied by this known as the radiation weighting factor. And we have another one which is talking about the equivalent dose rate. Now, there's a few things I wanted to talk about at this point. Number one, again, talk about definitions. Could be asked at some point about, I guess, the meaning of this radiation weighting factor. As it says here, it has no units. And that radiation weighting factor, it just allows us to compare the biological effect that different types of radiation have on a piece of tissue. Now, the values, if you had a question which included this H is D times omega R equation, if you had to use that equation, the values of omega R would be found in the data sheets at the start of the exam. You'll see there that for alpha it's equal to 20, again no units. Alpha would be 20, beta is 1, and gamma is 1. So basically that means that alpha is 20 times more likely to cause damage to body tissue than beta or gamma. And that's of course assuming that the absorbed dose due to each of those sources is the same. So if the absorbed dose due to, say, all 3 sources was the same, then alpha would likely do you 20 times, or likely be 20 times more damaging. Now, what else I can say about this? There is just one question, as I said, which I wanted to go over on. So I've just picked one of these equations. So make sure, give yourself time to try questions using all 4 of these equations. The last thing to say, I suppose, is about the units. Now what I have said up here is that T is time in seconds, but what I've not said is that only actually applies to this equation, where A is N over T. So if you were told that, let's say 100 nuclei decayed in a time of 2 seconds, and you had to work at the activity in becquerels, then of course the activity in becquerels would be 100 divided by 2 would of course be 50 becquerels. And in this one equation, like all the other equations we need to know in physics, time would be in seconds. But that's not the case for this one here. So this time could be years, days, hours, minutes, seconds. So it doesn't need to be in seconds. And the reason is that the unit for this is known as H dot. So H dot, as I said, is equivalent dose rate. And that can be in sieverts per second, sieverts per minute, sieverts per hour, day, year. In fact, it could even be in millisieverts per year, it could be in microsieverts per minute. Okay, so as I said, this T doesn't have to be in seconds. And that's one of the reasons as well. The question that I did pick was using this one equation. There we go. So nothing much else to say about those equations, but just make sure, as I say, give yourself some time before next week to try questions involving all 4 of these equations. Now, we have one last question, as I said, one last slide to look at. And, well, in fact, maybe there are 2, which is good because we do seem to be doing okay for time. So let me find the first one. There we go. So in fact, yes, there are 2. Get rid of the pointer, and it says a worker in a nuclear power plant spends 9 hours in an area where the equivalent dose rate is 190 microsieverts per hour. So there we go. As I was saying, time, I guess, doesn't need to be in seconds, and that in this equation, T would be, because H dot itself is in microsieverts per hour, then T, time, would be in hours. And it's okay, of course, that 9 hours would not, in this case, need to be changed to seconds. Now, of course, remember in the last slide, we saw the equation which was H dot is equal to H divided by T. And what we're being told in this equation, or this question, sorry, is the H dot. That's the 190 microsieverts per hour. And the T, that's the 9 hours. And we're actually being asked to work at H, the equivalent dose. So of course we want to rearrange that equation to give us H is equal to H dot times T, which is H dot is 190, micro is times 10 to the minus 6, and multiply that by time, which, as I said, because this is microsieverts per hour, of course time can be in hours. Now this is the first, as far as I remember, the first time we've looked to the calculator tonight. So 190, make sure of course you're using your own calculator, you'll know about this button, times 10 to the power of x. So 190 times 10 to the power of negative 6 multiplied by 9 gives me this 1.71 times 10 to the minus 3. Now what I did do is I converted those microsieverts to sieverts. So of course this would be now in sieverts. So 1.71 times 10 to the minus 3 sieverts. And there we have it. Now again, that's just one question on one of those 4 equations. If you're getting mixed up between I guess what the different letters signify in those equations, as I said, have a look at the website, download that file, help with relationship sheets, and try out some of these questions. Now, there is one last thing that I would like to look at, and that's this one here. So, it says, just click here, the diagram below illustrates 2 types of nuclear reaction. Name both and state the difference between the 2 reactions. Now, again, this is something that we talk about in higher physics, but we don't need to know in as much detail. And it's again something, I don't think I'll write this down on the paper. So again, make sure you know, we've spoken quite a few times tonight about definitions. So make sure you know the definition of a fission reaction and a fusion reaction. So what I'm not going to do, as I said, is write down the full definition, but hopefully we should know that reaction number 1 is a fission reaction. And if you were asked for a definition, then I guess what's happening, I'm going to find the pointer again. Now this obviously isn't labelled, but this signifies a neutron. And this could be, say, a uranium-235 nuclei. So when the neutron strikes this nuclei, or nucleus I should say, when the neutron strikes this nucleus, it splits into two nuclei, along with 2 or 3 neutrons. 1, 2, 3. So as I said, when struck by a neutron, a nucleus splits into 2 nuclei with 2 or 3 neutrons also being produced. Okay? As I said, in higher physics we do talk about fission and fusion, but in more detail. So as I said, reaction number 1, this is a fission reaction. Make sure, again, look through your notes and look for the definition of a fission reaction. Make sure that makes sense. And again, make sure that you can identify it from, say, a diagram like this. The one on the right hand side, however, that's a fusion reaction. So reaction number 2 is a fusion reaction. And of course, in a fusion reaction, that's the joining or the fusing of 2 nuclei to form a new, larger nucleus. Okay? So fission on the left, fusion on the right. And I guess what I've said quite a few times tonight is I pointed you towards, again, just reading through the notes, a lot of definitions to be aware of in this unit. But as I said, we did try one of those radiation equations. Make sure that you give yourself time to try more of those. And I guess for now, that's us. As I said, there's just one last lesson next Monday, just to mention a few things, to go through definitions, exam technique, talk about open-ended questions. That may be slightly shorter, maybe around about half an hour. We'll just see how long it takes at the time and how much time I've got available. So hopefully that's been of use. And again, thanks very much for listening, and we'll see you later.